How many men contributed their skill to enable the pilot of this airplane to dive and roll with confidence? Too many to mention them all. The hundreds of workers in the factory, of course. The military planners who stated the plane's requirements, and the airplane designer and his assistants who fashioned the design, incorporating both established aeronautical knowledge and the very latest aeronautical research information. One of the basic tools of the airplane designer is the research report, which contains results of theoretical and experimental investigations relating to the physics of flight. Wind tunnel recording tapes contain data for reports, which are the product of laboratories working to produce the scientific information upon which new aircraft designs will be based. The 3 research centers of the National Advisory Committee for Aeronautics are among the most important laboratories in the world for the production of aeronautical research information. The NACA is an agency of the federal government created to conduct and coordinate basic aeronautical research throughout the country. This is the Langley Aeronautical Laboratory near Hampton, Virginia. The first of the NACA research establishments. Its facilities include 20 major wind tunnels, 3 seaplane testing basins for hydrodynamic research, and special facilities for research in aircraft structures, helicopters, and pilotless aircraft. Here is the Ames Aeronautical Laboratory in California, located 40 miles south of San Francisco. This laboratory is concerned chiefly with aerodynamics, and its wind tunnels rank among the largest and fastest in the world. In Cleveland, Ohio, is located the Lewis Flight Propulsion Laboratory, specializing in propulsion research. Studies relating to complete engines and their components are conducted here. There are also extensive facilities for investigation of the basic chemistry of fuels and problems of flight operation, such as icing and fire prevention. But the primary facility for NACA research is the brain power and imagination of trained men. From the minds of these scientists and their equipment have come the elements of many of the major advances in aeronautics. In this film, you see some of this equipment and the men who work with it. Aerodynamic research below the speed of sound is conducted in a variety of wind tunnels suited to various needs. Although there are many kinds, these tunnels perform the same function of providing a controllable airstream and the means to measure reactions of a model to that airstream. Thus, the NACA's 36 principal wind tunnels can measure the characteristics of wings, bodies, and control surfaces through a broad range of flight speeds. Some tunnels operate at subsonic speeds, while others give data at nearsonic and supersonic speeds. In the working section of a typical low-speed tunnel, models are studied for stability and control characteristics at speeds throughout the subsonic range. At the control panel, engineers select the test conditions and study the important reactions of experimental configurations. Precise scale models of aircraft made in NACA shops and complete even to power installation are investigated for aerodynamic information. This is recorded on dials and gauges and provides the basis for aircraft design. The raw data are analyzed and interpreted for presentation in research reports. These reports, signed by the scientists who conducted the research, are distributed to aircraft designers throughout the country. An example of stability and control research is investigation of the spinning characteristics of aircraft, both in flight and in specially designed wind tunnels. In flight, research pilots execute deliberate spins, while instruments record the details of spinning, recovery, and the amount of control required. Inside the spin tunnel at Langley, scale models are used to determine the controlling factors in spins. Data from this work have made it possible to build safe spin characteristics into new aircraft designs. In a pressure wind tunnel, the engineer has at his command a special device to study the effects of model scale or size on airflow behavior as separate from effects of speed. By changing the air density while holding constant speed, or the reverse, these effects can be isolated and defined. Certain problems, such as how to achieve low-drag laminar flow over large airfoils and study of boundary layer, require this kind of tunnel. The NACA has several pressure tunnels covering a range of densities and speeds up to the speed of sound. The 40 by 80 foot tunnel at Ames can accommodate large research models and aircraft up to 70 feet in span. Together with the 30 by 60 foot tunnel at Langley, it provides information on stability and handling qualities at low speeds on new wing shapes and controls. Here, the canopy closes on a pilot who literally will fly standing still, while the results are observed and recorded on the tunnel balances and gauges. For answers to the special problems arising from flight near the speed of sound, the NACA has devised special techniques. Watch the dots representing air molecules speed up over the wing of this airplane. A local region of sonic and supersonic flow is formed on the wing, even though the airplane is traveling at subsonic speeds. Models mounted in this region can be studied at velocities from subsonic through the speed of sound to as much as 1.5 times sonic speed without a break. Instruments in the wing record aerodynamic reactions. In this way, models of aircraft, wings, and controls can be investigated in free flight through the speed range that is most difficult to cover in wind tunnels. Another technique is the use of pilotless aircraft. At Wallops Island off the Virginia coast, the NACA conducts research with rocket-powered models as a means of finding out how wings and controls work as they pass through the speed of sound. This model is used in study of automatic stability and control near sonic speed. However, the NACA has many wind tunnels, like this 16-foot tunnel at Ames, capable of providing accurate data very close to sonic speed. Together with the wing flow technique and the use of free-fall and rocket-powered models, they have provided the design information needed to build high-speed aircraft, like the Bell X-1 and the Douglas Sky Streak and Sky Rocket. The pattern you see taking shape is literally the shape of things to come. Already familiar to scientists peering through the side plates of supersonic tunnels, the pattern shows the shock waves that form when a body exceeds the speed of sound. A whole new set of physical laws comes into play, demanding new approaches and new equipment. The stage behind this shadow play is the test section of the 1 by 3 foot supersonic tunnel, one of 2 of this size at the Ames laboratory. The optical glass side plate is part of the precise apparatus used in making the airflow visible. In the 4 by 4 foot test section of this new supersonic tunnel at Langley, models twice the size previously used can be studied at over twice the speed of sound. This is one of 3 new supersonic tunnels, many times larger than those available before. And again, rocket-powered models are used to provide aerodynamic information in free flight at several times the speed of sound, while on the ground, radar crews man tracking apparatus to secure speed and flight path measurements. Other groups are busy at the telemeter receiving stations recording the technical information radioed back from the rocket model. At Langley Field, research is in progress on the structural problems imposed by high-speed flight. A variety of special machines have been devised, both to study individual structures and to provide answers helping to evolve general theory that can be applied to design problems. Various basic types of structure are put under stresses of all kinds to determine the effects and paths of stress flow. Along with thinner wings and forms for supersonic flight go demands for increased strength. These problems are challenging the best structural research men. Attainment of supersonic flight has been largely due to new propulsion systems. The new ranges of speed and altitude involved demand new and extensive research facilities. Here the cover closes on the 20-foot test section of the altitude wind tunnel at Cleveland. Inside, engine combinations of all kinds are run at simulated altitudes up to 50,000 feet and temperatures down to 50 below zero. By use of special ducting, engines can be studied at supersonic speeds as well as the tunnel's normal 500 miles an hour. With this and other altitude facilities, thermodynamic engineers are studying many types of jet systems, defining limits of operation and integrating other research on engine components. Another engine type under study is the ramjet. This apparently simple stovepipe-like device poses complicated problems of starting, combustion, and operation that demand research both on the ground and in flight. For supersonic flight data, a ramjet vehicle is carried aloft and released, telemetering information in flight up to 2.5 times the speed of sound. The aerodynamics of air inlets and diffusers are studied in propulsion wind tunnels, ranging from 2 to 4.5 times sonic speed. In the control room of the 8 by 6 foot supersonic tunnel, scientists will measure the factors determining performance of large engined and aircraft models up to twice the speed of sound. Mechanical air compression for turbine engines involves complicated airflow paths. The principles of blade shape and arrangement for different types of compressors are studied in detail. The product of this research is more accurate data for the design of compressors for even more powerful engines. When the fire is lighted in a turbojet, the turbine blades take a beating. They are raised to very high temperatures and subjected to enormous stresses at high rotational speeds. Higher allowable turbine temperature is an important factor leading to increased power. Attainment of successful blade cooling and development of heat-resistant materials are vital fields of research. The search for superior high-temperature materials has led to interesting combinations of metals and ceramics. Here, 2 test specimens are placed under stress in a furnace for a comparison of resistance to heat. The one on the left stands up well, but watch the one on the right. Hot. Hotter. Watch it break. The rocket engine, which gave us our first push beyond the speed of sound, is being investigated both for theoretical and practical possibilities. More powerful rocket fuels are being sought. Various types of engine and cooling systems are being studied to make possible the highest practicable thrust. While the fires burn in combustion chambers, thermodynamicists tackle the problems of releasing large amounts of heat in fast-moving air streams. This must be accomplished without slowing the airflow too much and without burning up the chamber. In satisfactory solution to the problems of combustion lies one key to more efficient and powerful jet engines. The diversity of new propulsion systems leads straight to the chemistry laboratory for the most suitable fuels. The energy release characteristics and availability of all kinds of fuels are studied, and this research is related in turn to the combustion and cooling processes. With the aid of new electronic equipment, physical chemists are probing into the molecule and inside the atom for new sources of energy. Early aeronautical research was conducted principally with airplanes in flight, and although the NACA today operates many tunnels, flight research remains the final check on laboratory study. Also, there is certain flight information that no ground device can yet provide, such as maneuvering loads and accurate data at the speed of sound. One notable contribution of NACA flight research is the thermal ice prevention system. This C-46, fitted with hot air ducts and a test airfoil atop the fuselage, has been systematically flown in icing weather to prove the system. Exhaust-heated air is circulated through wing and tail leading edges, while propellers are protected with electrically heated shoes. Various adaptations are becoming standard on new aircraft. In the air on a research flight, This is what the camera sees of a test operation of thermal ice removal. At Muroc Air Base, important research is in progress on flight at transonic speeds. The Bell X-1 takes on its load of fuel and liquid oxygen for a research flight above the speed of sound. 2 of these airplanes are being flown by NACA and Air Force pilots. The technique of carrying the X-1 aloft was developed to conserve the rocket fuel for high-speed flight at high altitude. Release is accomplished with bomb drop technique. The X-1 carries 500 pounds of NACA flight research instruments to record desired details of flight above the speed of sound. The X-1 is part of a larger cooperative research program in which the NACA, the military, and the nation's aircraft industry are participating. The transonic and supersonic aircraft built by Douglas for the Navy and NACA are also being used in this project. Vital information on piloted flight through and above the speed of sound is resulting from this work. In the air, the flight crew prepares for the drop. When the mothership reaches the proper altitude, the pilot climbs down into the bomb bay. From there, he descends into the X-1 through a small hatch, which is closed after him. On a synchronized count with the pilot, the bombardier gets ready. 3, 2, 1, and away. The X-1 drops into space, and the pilot turns on one of the rockets to pick up speed. A photographic chase airplane trails the X-1 to make a film record of the start of the flight. On the ground, speed checkers track the airplane as the X-1 turns on the heat and streaks away to obtain important new data. Through this and other means, the unknown is probed for new knowledge of flight. Together with a vigorous aircraft industry and alert operating organizations, such as the military forces and airlines, the NACA labors to attain better and safer aircraft for a better and safer world. Plane designer and his assistants who fashioned the design, incorporating both established aeronautical knowledge and the very latest aeronautical research information. One of the basic tools of the airplane designer is the research report, which contains results of theoretical and experimental investigations relating to the physics of flight. Wind tunnel recording tapes contain data for reports, which are the product of laboratories working to produce the scientific information upon which new aircraft designs will be based. The 3 research centers of the National Advisory Committee for Aeronautics are among the most important laboratories in the world for the production of aeronautical research information. The NACA is an agency of the federal government created to conduct and coordinate basic aeronautical research throughout the country. This is the Langley Aeronautical Laboratory near Hampton, Virginia. The first of the NACA research establishments, its facilities include 20 major wind tunnels, 3 seaplane testing basins for hydrodynamic research, and special facilities for research in aircraft structures. How many men contributed their skill to enable the pilot of this airplane to dive and roll with confidence? Too many to mention them all. The hundreds of workers in the factory, of course, the military planners who stated the plane's requirements, and the